All right, welcome to our free GMAT prep hour for April 23rd, 2023. Today's topic is something I've had a lot of demand for over the years, but also a lot of people would be happy to never talk about. So we'll see what you think. The topic for today is combinatorics. This is often considered one of the hardest topics on the GMAT, but I also just think of it as fancy counting. And if we can count, then we can build up to doing some pretty hard combinatorics problems. So I want to build from the fundamentals to some harder applications. If this is something you're already cozy with, forgive me. We'll try to make it all make sense and then put it together so you can even handle things that are pretty challenging. Depending on how things go today, we could do a follow-up session with more advanced applications, or we'll see how far we go with it in our hour together today. So this is what I'm going to work on. This is a topic that's annoying enough that we've actually kicked it out of our main class. At some point we decided, look, it's kind of a steep learning curve for people and we only have so many hours together. And although people kind of clamor for help with it because it's difficult, we just would rather people focus on more of the fundamentals, your algebra skills, your fractions, decimals, rates and work, picking numbers, stats. However, it's a pretty good chance you're going to see one or more combinatorics problems in your test, especially if you're doing fairly well in quant. And at their easiest, they're not bad at all. At their hardest, they're pretty awful, but we want to give you some tools to manage them. So we're not going to try to give you the hardest combinatorics problem you'll ever see today, but I want to make sure you have the tools to approach them with confidence if you choose to pursue this area. And if you decide after today that, combinatorics is just not for you, live and learn, and that's fine. Unless you're trying to get a perfect quant score, which is not most of our goals, you can afford to choose a couple of smaller topics to just not do when you see them. Just next, and that's an important part of your GMAT strategy. Okay. Just a reminder for folks who are attending live, you have a chance to win all this loot. So I put that link in the chat. And if you're attending, if you're watching a recording, then we may have this again for future in-person events too. You can check it out when you stop by in person. In-person, online, you know what I mean. All right, so let's take a look at what we're talking about when we're doing combinatorics. We're talking about fancy ways to count. So let me start asking you some questions. Let's say I've got a menu. I've got 6 kinds of pasta and 8 kinds of sauce. And I want to know how many different combos I can make of pasta and sauce. This is where these problems have their base, right? They're counting problems. How many ways can you do things? How many groups, teams, selections can you make? So how would we answer this? How many ways are there to combine 6 kinds of pasta and 8 kinds of sauce? Well, the idea here is that when you have multiple decisions to make, all you have to do is multiply them. Okay, so we'd say 6 kinds of pasta, 8 kinds of sauce. That's 48 possible combos, right? If you think about it as like pasta A with any of the 8 sauces, pasta B with any of the 8, pasta C, etc. So 6 groups of 8 or 8 groups of 6. This gets us something we call the fundamental counting principle. When you have several independent choices to make, you multiply them together, and that's going to give you the total number of possibilities. Okay, so 6 of this, 8 of that gives you 48. Do the same thing if you're, say, putting together outfits, right? So maybe I have 3 shirts. Oh, pardon me. 3 shirts, 6 pairs of pants, and 4 pairs of shoes. And if I look at the combos I can make of those things, I'd say, all right, well, then that means 3 times 6 is 18. 18 times 4 is 72 possible outfits if every single different switch is an outfit. And anything else I throw in there is going to multiply it again, right? If I choose to wear a hat or not, now that's 72 times 2. 144 possible outfits, with an outfit meaning like, hey, I could wear all these clothes with a hat, or I could wear all these clothes without a hat, and that's 2 different outfits. Okay. Possibile. Typing is interesting. Okay, questions on that? How are you feeling about how that works? One thing that connects combinatorics to another common area of probability is the idea of or versus and. So some people will ask me like, why not add? Right? 6 plus 8 is 14 combos. Okay? And the trick to that is that they wouldn't be combos, they'd be separate things, right? This is what we do if we wanted just one thing, right? Either pasta or sauce, right? It'd be like if I said, hey, there's 6 American wines you could choose from, and there's 8 French wines you could choose from. And you say, all right, so there's 14 wines. And if I'm just going to have one wine, there's 14 choices. But if I'm going to have an American wine and a French wine, then there's 48 different combinations of things that I could have, right? And so this gets into the same idea that we have with probability, is that generally when we see an and, we multiply. And there's some exceptions and twists and things like that. But when we see an or, we add. So if we said, hey, I want pasta and sauce, I'm going to do 6 times 8 is 48. Whereas if it's pasta or sauce, it's kind of a weird menu offering, right? If it was, hey, you can choose one of 6 kind of pasta, or if you prefer, you can just have a cup of sauce, right? It's a little weird. It might make more sense with the wines, French or American. Then you'd have 14 individual choices. Okay, that all right? Okay, so then how do we build on that to do harder problems? Let's say I have something like this. I want to make a code, and the code is going to be a 4-digit code. Any 4 digits from 0 to 9, like a password. I want to know how many different codes I can make. Well, in that case, I can think of each digit of the code as a set of possibilities, and I can still use my fundamental counting principle. I can set up slots. We often call this the slot method. And I can just fill it in. I can say, all right, well, for my first digit of my code, I can do whatever I want, right? I can put any number. So how many possibilities do I have to put in that first spot? Yeah, I can put 10, right? There's no restriction made about what the code has to look like. I can start with anything I want. I have 10, right? What about for my second spot? Any restriction there? A lot of times people will say, how do I know if I can reuse a digit? And sometimes my smart aleck answer to questions like that is they'll tell you, right? Now they don't always say you can do something. Sometimes they say you can't do something. But here they just said 4 digits. They didn't say anything about whether we could reuse them or not. So if they don't say we can't, then it's just 10 times 10 times 10 times 10. Right? So I can think about this in terms of restrictions, or I could just say, oh, this is going to be however you want to call that, 10 to the 4th, or of course you could just say 10,000. 10,000 different codes. Okay. So we can use that slot method. Now that one was not super crazy, but we can look then at variations and still build those on the slot method. So one variation would be, instead of just any code I want, I have to create a 4-digit even integer. So we have to think about what kind of changes does this require? Okay. Looking at my first digit on the left, what restriction do I now have on what that digit can be? The very first number, the 10,000th place. What restriction do I have on what that can be? If I want it to actually be an integer, an actual 4-digit integer, I can't start with a 0, right? Because 0001 is an integer, but it's not a 4-digit integer. It's a 1-digit integer. It's just the same as 1. So that can't be what I want. So I'd have to look at the first digit and say, I don't have 10 choices anymore. I only have 9 because I can't put 0 in that first place. Whereas in this second place, I can put what I want. I could put a 0 there. I could put a 0 here. I've got all my choices there. What about for my final digit? My ones place. How many different digits are available to me for that? I want to make an even number. So half the numbers are off limits to me. I can't use any odds. I can end in 0, 2, 4, 6, 8. So I got 5. All right, so I would find it like this. So it'd be a much smaller number, just a little under half, right? Which kind of intuitively might make sense. You might say, well, if I can make 10,000 codes, well, half of those are going to represent evens and half are going to represent odds. So about 5,000 would be even. But then I'm also cutting out anything that starts with a leading 0. And about 1/10 of them will start with a leading 0. And so if I chop it down to 5,000 and take off 1/10 of that, that's 4,500. Right. So you can also sort of think about them, do a little logic. This is though where it gets a little annoying. And this is where some people don't love combinatorics, because even though it's really just fancy counting, just finding ways to count and keep track of things, it's very easy to forget one thing, to leave one part out. Right. It's hard enough when we're just doing arithmetic. I divide by 7, but I forget to multiply by 3 or whatever it is. Right. But then when I have all these pieces to think about, often what happens when we miss these, and almost all of us have missed some of these. I've certainly had some where I went back and went, oh yeah, I didn't divide by that. We just overlook one piece, or we don't think about it, or we treat two things as the same when they're really different. Right? So it gets a little woolly to think about. But once we get past that, then it just becomes, good old arithmetic again. So this would be 4,500. And, of course, I'm giving you I'm giving you questions without multiple choice answers, which the GMAT won't do. And so one thing you can use to your advantage is to narrow things down. So for instance, if I saw answer choices and, A looked like 10,000, I'd say, well, no, 10,000 would be if I had no restrictions at all. And then if I said, hey, it'd just be around 5,000, then even something like 6,600 would be too big. And then maybe I see C and it is 5,000 and I go, well, would it be exactly half? So yeah, half of the numbers are even and half of the numbers are odd. That seems about right. But then if I think about, well, are there any numbers that are left out, like ones with a leading 0, then I might know, oh, it's got to be a little less than half. So then if I saw D was 4,500, I would already have caught out, I would have cut out A and B with very high confidence, like no way, no way. Then I'd say, I don't think it's C. Then I look at E and I see something like, I don't know, something weird, right? 450 or 1,500. And I go, no, it's a much larger fraction than that. That can't be right. And so I could end up picking D, even if I wasn't sure that I could calculate this. Sometimes today we'll generate some answers that'll create very big numbers, and I might not feel cozy calculating those, or I might take a long time, or I might make a mistake. Sometimes we can use some of this logical process to narrow things down so that if I do make a mistake, I catch it. Other times the answers might actually be in a format that doesn't have to be calculated. It maybe just shows the factors. And you'll see that repeatedly as you do the GMAT. Sometimes if the answer is pretty tough, it'll just be in a form where they show you a number and it's square, but they don't actually make you square it. Or they give you a factorial, but you don't have to multiply out the factorial. So sometimes they save you some labor. Same thing if your answer is something like 2 to the 30th, you're not expected to find out what that is. Your answer is just going to be 2 to the 30th, and you're going to leave it there. Okay. Questions on that before we try another variation? Okay. So another variation we can see, and this is an important one for the stuff we're going to do afterwards, is what about when they ask you to make your items distinct, which is a fancy way of saying different from each other, right? So now I want to create the same 4-digit code as before. But now I have all the digits 0 to 9 available, but they have to be distinct. In other words, I can't use the same digit twice, no doubles or triples, quadruples. So what does that do to my slots. So I can start with my same setup. And I can go in there and say, all right, well, for my first slot, it seems like I have all the freedom in the world. And by the way, I'm starting on the left. I could just as well start on the right. So for instance, when I was doing the even numbers, I could have said, well, I want to end with an even number. So there's 5 of those. And then I can have anything I want in the middle. There's no reason I have to start from the left, but that's what I've been just doing because it's usually simpler, but it's not always simpler. So here I could say I'm going to start with any number I want. It's not so that doesn't say it has to be an actual 4-digit integer. So I can start with 0 if I want. And I haven't used up anything, so I'll go there. But now I'll say, all right, going to the second place, I've already used up one of my digits. I don't know which one I've used. I don't know if I've started with 1 or 2 or 9 or what have you. But one of them's accounted for. You can think of it as like a slip of paper pulled out of the hat or something, right? So then I could say, all right, there are 9 choices remaining. And then 8, and then 7. And if I kept going, if I was creating a longer code, I would eventually run out of numbers, right? You can't, of course, make longer than a 10-digit code if you can only use digits from 0 to 9 each once, right? Just like, if you have a bunch of Scrabble tiles, you can't make a word longer than the number of tiles you have. Well, I guess if you're playing Scrabble, you can put it on the board. You know what I mean, right? I can't make more slots than I have elements. Okay. So I would get something like this, 10, 9, 8, 7. And this is the basis for most of what we're going to do in combinatorics. This idea of counting down that gets us to the idea of factorials. Okay. So if you have any questions or troubles about why we're counting down, let me know. Otherwise, I'll keep moving. What if I had only the digits 1 to 4 to choose from? You can see I'd run out pretty fast. I'd say, okay, well, let's see. I've got 4 digits I could choose from for this first spot. And 3 for the second, 3 for the third. Can't talk. 3 for the second, 2 for the third, flip those. And then a really common situation you find when you're counting down is that if you have the same number of items as spots, by the time it's the end, there's only one choice left. Right? It's like if every other kid gets to pick, their seat before you, right? Then when it's your turn to pick, you just have to sit at whatever seat is left, right? So we have this thing of, okay, I've chosen out of 4 digits, I picked one. Now I got 3 left. I picked one. Now I got 2 left, picked one. I just got the 1 left. I just have to put whatever is left. Okay. And this creates what we're going to use for the rest of today, which is the idea of a factorial, right? And a factorial tells us that, hey, when you have n elements and n spots, you can arrange those in n factorial ways, which is factorial is just a way of saying 4 factorial is 4 times 3 times 2 times 1. I always write the 1 because I'm kind of OCD about that, but it's not necessary. I could just say, leave the 1 out. 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, if you want, times 1. If I have something that's like a variable, I don't know what it is. All I know is it's going to be x times x minus 1 times x minus 2 all the way down to times 1, right? Okay. And so this is true anytime you have things that are getting arranged a given way, right? So for instance, I could say there are 20 kids in a class. And I want to know how many ways can they line up. And these all assume that I think it's different when you're in front of me versus I'm in front of you. I care about the order. That's what I mean by line up. If it just means all the 20 kids line up, there's just one way to do it. Line up or don't, right? But if I care who's first, second, third, fourth, fifth, then there's 20 factorial ways, right? Because I don't want to figure out what 20 factorial is. But I'd say, hey, there's any of the 20 kids could be in the first spot or the last spot, however you want to count it. Any of the 19 remaining kids could be there, etc., all the way down times 2 times 1, right? Similarly, if I'm doing a 1-to-1 correspondence, right? There are 10 employees and 10 offices. How many assignments of employee to office can I make? A common mistake people make here is to say 10 times 10 is 100. And that's not right at all. 10 times 10 would give me how many ways to take one employee and put them in one office. Oh, I'm going to take Jen and she's going to go in office 5, right? Okay, there I could have made 100 such choices. But what I'm saying is, hey, for office 1, any of the 10 people could go in there. Now, office 1's taken. Who's going to go in office 2? Any of the 9 people could go there, right? All the way down. So that's also 10 factorial. And this is the basis of most of what we do in combinatorics. Okay, how's that feeling? Okay. Okay. One thing I'll also mention here is that it's very easy to create a problem that I'm going to struggle to solve. And so one of the reasons that this topic could be hard is we don't always recognize the difficulty. I'll give you a problem that we're not going to solve right now because it involves more complexity than we actually might want to mess with. So what if I combined the two variations I did earlier and said, I want a 4-digit even number with all different digits. How many are there? That's surprisingly hard to do. I'm not saying that we can't solve it or that you couldn't solve it, and we could play with it, but it's actually pretty hard. And if you were not feeling great about this type of topic, I would get right out of there. Why? Well, you could say, okay, looking at the slot method, I know a 4-digit number has to start with something other than 0. So there's 9 possibilities there. And then I could say, all right, well, then let's see. How many are left for the middle? There's 10 that could go in the next slot because it could be anything. But wait, hold on. No, not 10. I can't use whatever I just used for the first one. So that's 9. That would leave 8 here. But then how many can go in the last spot? Well, I don't know. I know it needs to be even, so I want to say 5, but I don't know if all 5 of the evens are available, right? Maybe I chose some even numbers for the first 3. So do I bring it down to 2? Have I used all the even numbers or have I not? It becomes actually really complicated. And so I might have to break this into pieces. I might have to think about what happens if I use a number, like for instance, what happens if I use 0 here, and then I can use anything I want of the remainder over here? Or what happens if I use, say, the digit 2 here? Whoops, that's a 1. And then this digit can't be 0 or 2, and now there's only 8. So there's actually a lot of complexity. I might have to break this down into a few cases. So I'm not saying there's no ways to do it or that you couldn't do this in 2 minutes, but it becomes surprisingly hard, and that's where the complexity can come in. So one thing that's useful to recognize is, when is there more stuff than I can or want to deal with? And I think that's really wise on this test as a whole. It's just like the rest of life. If you're given a job to do, or you're trying to do a physical task, you're trying to lift a weight, when do you say, nope, 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 I'm not doing that? Right? You probably have that thing with physical tasks, right? You try to lift something, whether you're in the gym or you're just, in the house, you're trying to lift a shelf or something like that. And you start to pick it up and you go, oh, no, 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 no. Like, I'm going to hurt myself at, if I could even move it at all, right? It's harder to tell that sometimes with mental tasks. We think, oh, this is easy. And then we get in there and it blows up in our face. And so diagnosing is very important. And like I said, getting rid of things, skipping things is very important to this test. Okay, having said that, let's build to questions that look more like what you'll see on the GMAT. So what you'll usually see is you're selecting out of a pool. So you'll see something like this. 8 people compete in a contest. Prizes are awarded for first, second, and third place. How many different ways can the prizes be awarded? So if I want to do something like this, I can still use my slot method, right? I can still say, okay, I've got 8 people. I want to choose the first place. Well, let's see, that can be any of the 8 people. Once I've chosen one of those people for first place, I can have any of the people be second place and any of the people be 6th. And this is true whether it's, a race and, whoever is first wins, or whether it's I'm just choosing arbitrarily who wins, doesn't matter. There's this many ways for it to happen, assuming that they're all equal, right? If it's an actual race and one person's, super fast, then of course, maybe they'll always win, right? That's another story, but the GMAT's not going to give you that kind of thing. It's going to generally have things where all the elements get treated the same. And if they want you to treat one differently, they'll add a very specific constraint. They'll say like, how many groups can you make where Dan and Linda aren't together? Or how many groups can you make where at least one of the people has management experience? And they'll have to have like laid that out very, very clearly. We can talk about some of those variations. Okay, so this is still the slot method. This is still really the same thing that we've been doing. What I want to show is that this is equivalent to working with a factorial, a pair of factorials. So if we think of this as 876, what's interesting to notice is that that's the beginning of a factorial. It's just missing the 5, 4, 3, 2, 1. And this, if you can understand this, you're going to understand most of what you need for combinatorics. Because we could say, all right, well, what happened to the 5, 4, 3, 2, 1 out of my 8? If I had 8 places, then I could say, all right, there's 8 factorial ways for people to finish the race. There's 8 people who could finish first. And then once someone's finished first, there's 7 remaining people who could finish second. And then there's 6 remaining people who can finish third and 5 remaining who could finish fourth, et cetera, all the way down. But what we're saying is, hey, after third place, we stop paying attention. We don't care anymore. There's no, as they say, there's no prize for fourth place, right? We're not looking at that. And so it doesn't matter if I come in fourth and you come in fifth, or if you come in fourth and I come in fifth, those are the same outcome for the purpose of this problem, because we only care about the first 8 places. And so there's a lot of complexity that we're ignoring. If I wanted to put 8 people in order, there's 8 factorial ways to do it. But that's, what is this? 5 factorial is, let's see, 3 times 2 is 6, times 4 is 24, times 5 is 120. That's 120 times too big. So the number of ways to arrange 8 people is 120 times larger, or 120 times the size of the number of ways to arrange 3 out of the 8. And so the way we can think of this, and this will help us bridge to different kinds of combinatorics problems, is that we're going to be dividing out our outs. And what I mean by outs are the people or the items that we're not selecting. And if we think of it that way, we're going to get the same result that we'd get with our slot method. And then we don't necessarily always have to write down the slots. I could just say in general, okay, I want to hire 4 people. I interview 12, right? How many groups can I make, right, of hires? And the important thing here is that I'm not saying, hey, I'm going to hire you to be the manager and you to be the security guard and you to be this, right? I'm just saying I'm going to hire 4 people. Maybe I'm hiring 4 people to work security at the concert tonight, or I'm hiring 4 entry-level realtors or whatever it is, right? But they're all the same for my purpose, right? They're different people, but the position's the same. So I don't really care what happens to the people I bring in. Now, that's going to mean that I care not just about the people, let me say that better. That's going to mean that I'm disregarding not just who goes out, but also really I don't care that much about what happens when people are in. So we're going to come back to this variation in a second. Let's make it distinct, right? I want to hire 4 managers for 4 different branch offices. So now I'm going to say, okay, I care, when I hire you, I care which branch office you're going to run. Are you running Pittsburgh? Are you running Philadelphia? Like, which one are you in? Okay. But I could say, well, there'd be 12 factorial ways to like arrange if I had 12 people in 12 offices. But I don't care about all the people who I don't hire. And so I'm going to think of this as 12, 11, 10, 9. So the slot method and the factorial method are going to give me the same thing. I'm going to say the number of ways I can pick 4 different people out of 12 and leave out 8 is going to be 12, 11, 10, 9. So the short version is divide by your outs factorial. take your pool on top and divide by your outs. That's my formula. Okay, so that's just stuff to process if this is new. Any questions on that? Okay. So we'll come back to what happens in a moment, but what happens if I don't care what the person does once I hire them? Like they're all the same, they're all the same position. So let's build on that a little bit. I've got 8 people in a contest again. But now I'm not putting them in first, second, third place. Instead, I'm simply saying 3 people get prizes. So that was just different from what we had before. Just like with I hire 4 realtors, I hire 4 security guards. I'm just picking 3 people. And once I pick them, I'm not saying, hey, you win this prize and you win that prize. You just each win a prize. Maybe you each win a $20 gift card or something like that, right? So it doesn't matter which winner you are. And that means I'm going to create a lot of redundancy, right? If I choose A, B, and C to win, that's the same as C, B, and A, or B, A, and C. In the Olympics, that would be different, right? If you're runner A, you want to be first. You don't want to be third or second, right? And those are all different. And even if you're first, it would be different if B is after you and then C, or if C is after you, then B. And in fact, for any 3 people, there's 6 factorial ways, or not 6 factorial, 6 ways, 3 factorial ways to arrange them. So what do we do if the ins are all the same, if they're getting treated all the same, we don't care what happens to you once you're in, then we're also going to divide by the factorial of the ins. So you're always going to divide by the outs. You may divide by the ins. Okay, so in this case, we'd say I've got 8 factorial people to arrange, right? 8 factorial is based on the number of people I'm arranging. I don't care about the outs because they're not getting prizes, but I also don't care about the ins. And so that would look like this. If I wrote it all out, I'd say 8 times 7 times 6 times 5 times 4 times 3 times 2. I'll keep being OCD and writing the 1. You really don't need to. And then if you get used to doing the 5, 4, 3, 2, 1, you'll know that those cancel. But I'm also going to divide by 3, 2, 1, which is 6. So I can then also cancel this. I have 1/6 as many possibilities as when I was putting them in order. It's just this is a much more countable number. It's 56. So the basic idea is, and the reason I put a question mark, it's funny to have an exclamation mark, question mark. It looks like I'm befuddled, right? I hope that you're not. I'm taking that pool that I'm pulling from on the top. I'm dividing by the factorial of the outs all the time because I never care what happens to the people who I don't hire, who don't win, the kids that don't get in line, whatever it is. I'm not worried about how that's handled, how they're arranged. But I may not care about the ones that are in either. Not that I'm not hiring them or not selecting them or they don't win a prize or they're not wonderful people or whatever it is, but simply that once I have selected them, I'm not arranging them any further. So the key phrase here is you're not arranging them further. If all I care about is if you're in or you're out, then I divide by the factorial of each of those. And I think the part that's most confusing for people, I've had people scoring in the 700s who are still like, this doesn't make sense to me. So if you don't feel great about it, you have company. The thing that people get confused about is that if you don't care about a group, you do show that in the equation. You do divide by it because you're making the number smaller. So I want to look at some concrete examples of this because I know that's a lot to process. And so I hope folks will jump in the chat and let me know if this is working, if they have questions, because I want to make sure this feels all right. So let's look at a couple examples. Right. In one case, I have 12 interviewees. I hire 4 to be realtors. In another case, I have 12 interviewees. I hire, I'll do this. I hire a manager, a realtor, and a security guard. Okay, so what would these look like? In both cases, I'm going to expect a fraction. And in both cases, I'm going to put my pool on the top. This is kind of the standard. And the idea of this is I'm always building down from this pool, right? Or breaking down from this pool. Because if I had 12 people, A, B, C, D, E, F, G, H, I, J, K, L, right? If I had 12 people to pick from, I could say, well, I could pick any of the 12 people for my first spot and any of the 11 for my second spot all the way down, right? Until the last person has to take whatever's left. But I don't really care what happens to most of the people, right? In one of the cases, I'm hiring 4 to be realtors. So what happens to the 8 people who I don't hire? I don't care. I'm not going to say, well, I'm going to not hire Bob and then not hire Carol, right? No, it's the same thing as if I say I'm not going to hire Carol, not going to hire Bob. I'm not going to worry about any of that. So I divide by that. But what about the 4 who get hired to be realtors? Am I doing any arrangement of that group? Do I care where they go? In this case, I don't. Right? I don't care what happens to the 4 who I hire either. I just hire them or I don't. Whereas in the other case, in the 12 interviewees, manager, realtor, security guard, I don't care what happens to the 9 people I don't pick, right? There's 9 people who don't get hired. I don't worry about that. But wait a second. For the other 3, they're not just a group of 3. It matters whether you're the manager or you're the security guard. Those are different jobs. And so I'm not going to divide by this, right? So if you don't care, you do divide out. So here, I never care about the outs. I sometimes care about the ends. If I care about them, I do not see their number there. I don't divide them out. It's kind of a weird thing to get used to, but we can do this. Let me give you some variations. What if I interview 12 and hire 8 realtors? And I think, well, it's kind of the same problem set up, right? I'm digging 12 on the top and I'm taking my outs. But the interesting thing is, if I hire 8, then I have 8 ins. I don't care what happens to those. The number of ways to hire 4 and the number of ways to hire 8 is the same. Anytime I'm just putting people into 2 groups, it doesn't really matter which is the in group and which is the out group. For instance, I could think of it as, there's 4 people on team A and 8 people on team B. But the math doesn't care what I call team A and team B. I could just as well have said there's 8 people on team A and 4 people on team B. It's just making it into 2 groups. So in general, if I have one group of ins and one group of outs and I switch their labels, the number of ways to do it would be the same. So there's just as many ways to hire 4 as to hire 8. There's just as many ways to hire 5 as to hire 7. There's just as many ways to hire 6 as to hire 6. Okay, those are the same. There's just as many ways to hire 1 as to hire 11. Right? In fact, that's a common thing that shows up. If I have to choose 11 of the 12, I'm really just choosing which one I don't want. It's like if there's 5 appetizers and you're going to order 4, you just say, okay, so which appetizer don't you want to try, right? Because you're going to get everything else, right? So there's 5 ways to do it. You could not get 1, not get 2, et cetera, up to 5. Whereas it's different if I'm going to hire more people here, right? If I have 12 interviewees, and I'm hiring managers for 9 different offices, then there's only 3 people I don't care about, right? I don't care who is out, but I absolutely do care about the 9 offices, right? If I hire you, it's different to hire you and put you in New York versus to hire you and put you in Sacramento. Those are different things. To me, to you, it's just a different placement. And so I'm not going to divide by that 9 factorial. And that's what we have to get used to. If I do care about where you go, then I don't divide your group out. The people who are getting hired, that factorial doesn't go out because it matters. Once I hire you, I'm deciding where to go. Same thing if I'm putting you on a basketball team. Am I just selecting a basketball team, or am I saying, hey, you're on the team and you're going to play center? Right? If I'm going to do that, I don't divide out because I'm concerned about counting that number of possibilities. Okay, how are we feeling? So let's test a few cases. See if we can recognize which one we're dealing with, and then we'll look at maybe combining them. And then you're going to have most of the tools you need to handle combinatorics on the GMAT. Okay. So I'll just give you a few cases and you see if you can see which one we're dealing with. Okay. So I'll say, there are 5 different desserts. I want to pick 2 to try. There are 5 different entrees. I want to pick 1 to eat here and 1 to take home. There are 5 different types of cookie. I want to try 1 cookie each day, Monday to Friday. So in each case, we want to think about how many ways there are to do it. So take a moment to try setting these up and we'll come back and check. All right, let's see how we did with this. So for all of these, I'm going to have a baseline of 5 factorial that I'm going to kind of break down from. And the one that's going to be the plain 5 factorial is the bottom one, right? This one will just be 5 factorial because we are saying, hey, on Monday, I could choose any of the 5 kinds of cookie. I should have said more clearly, try 1 different kind of cookie. Otherwise, it would be 5, well, it'd be 5 to the 5th, right? It would be 5 times 5 times 5 times 5 times 5. So sorry, 1 different type of cookie, right? Then that would be 5, 4, 3, 2, and then on Friday I'm having whatever I didn't have before. Okay. So that would be my baseline. Then if I say, okay, I have 5 different desserts and I want to pick 2, then I'm saying the same thing. I can pick any of the 5 and then I pick any of the 4. But I don't care about the 3 that I'm not trying. So I don't need to do 5, 4, 3, 2, 1. I could just do 5, 4. So I'm dividing by 3 factorial. I'm dividing by the outs. Additionally, then I'd say, hold on, what about the 2 that I do try? Is it an ordered thing? Am I saying, oh, first I'm going to have ice cream and then I'll have a Napoleon or vice versa, or I'll have dessert A, then dessert B? No, they didn't say anything about that. So I'm going to divide that out too. I don't care about the order because they didn't tell me, oh, I need to create a dessert schedule, or I need to have one on Monday or one on Tuesday, or I'm going to have one and my partner is going to have another, or anything like that. So if they didn't say that we care how they're arranged, and they didn't give me any language to indicate that, then it doesn't matter. So I just do 5 times 4 over 2, right? The 3, 2, 1 cancels, and I get 10 ways. Whereas here, I do care about which is which, because I've got 5 factorial to break down. I don't care about the ones that are out, but I do care. If I wanted to be really nerdy about it, I could call this 1 factorial. I could say each group is a 1 factorial. But those, of course, don't do anything, so I can just ignore them. So this, you'll notice, has twice as many possibilities. And that might make a certain sense, because you could say, oh, well, there's twice as many ways. If there's 10 ways to choose 2 desserts, for each of those 10 ways, I could choose whether to have one now and one later, or the other way around, right? If I got cookies and pie, I could eat the cookies now and pie later, or pie now and cookies later. That doubles my number of possibilities. So the maximum number of possibilities is 5, 4, 3, 2, 1, right? As we've seen, this is 120 different ways. So there's 120 different ways if I'm choosing all the 5 things in some different order. It becomes less if I'm only choosing 3 of the things, but 2 of the things, but the 2 that are left, I still do care about the order. Which of the 5 I'm going to have first? Which of the 4 remaining am I going to have second? Okay. And again, the GMAT will wear things very carefully, and I wasn't super cautious on that second one. I could have said one different one to take home, not the same. Otherwise, of course, it would be 5 times 5. Maybe I just want pie again. And then it narrows that even further with the one on the top. There's 5 different desserts. I just want 2 to try. I don't care about the order, so it's half as many. Okay, questions about that? Then we can do a few variations. So one variation would be that there's more than just an in and an out group. I could say I interview 12 people again. I hire 1 manager, 2 receptionists, and 3 security guards. So now I could do the same kind of thing on the top, 12 factorial. And I could say, all right, so it looks like I'm hiring 6 people. So I don't care what happens to the 6 people I don't hire. So I'll divide by that factorial. What about the manager, receptionist, and security guard? Surely it matters which position you're in, right? If I hire you, are you going to be a manager or are you not, right? But within those pools, I don't care which security guard you are, which receptionist, because they didn't say anything. If they said something like, we need security guards for the 1st, 2nd, and 3rd floors, or we need a lead security guard, an assistant, and an alternate or something, that would be one thing. Then those are different spots, right? Just like if I have a cookie today or if I have it tomorrow, it's different spots. But if the receptionists and the security guards are within their groups are interchangeable, then I would just put factorials of all the groups. I could put the 1 just to be picky about it, but it would look like that. And the numbers would get pretty large. So the answer might just be something like this, or it might be partially broken down. So I can do 12, 11, 10, 9, 8, 7. I don't need to do the 6 down because that cancels from the previous. And then 3, 2, 1 is 6. And so I would then say, okay, well, let's see, I can maybe cancel a 6 out of a 12 and get a 2. That's going to be a lot to calculate. I'm not going to do that right now. If you were doing this for the GRE, they give you a calculator. Long term, the GMAT's going to have a calculator for some portions, I think. So that'll be interesting. But for now, we're not worried about doing calculator stuff. So this is maybe more than they'd expect you to multiply out on a real GMAT problem. But this is the idea behind it. Other variations you can see are multiple combinations, right? So what if they said there are 5 cookies, pick 2, but then there's also 5 gift boxes, or let's say 10 gift boxes. Pick 2 for those, right? So it's like, hey, I've got 2 different cookies I can pick, and then I'm going to pick 2 different gift boxes to put them in. That gets more complicated. So I'd have to just do 5 choose 2 times 10 choose 2 and do those individual combinations. So I'd say, all right, there's 5 cookies. I don't care about the outs. Didn't say I care about the ins. It didn't say cookie 1 and cookie 2. And then I'm also going to do 10 gift boxes. I don't care about the outs. I don't care about the ins or how they're ordered. And so I just multiply those together. Right? What about if I say there's 5 team members? Let me do it more. Let me say there's 7 team members. We want to build a group of 3. However, Bob and Carol cannot work together. Right? How many ways can we do that? This is a common wrinkle you might see on a harder GMAT question. So we can start with the baseline. 7 people. I don't care about the outs. And I don't care about the ins, right? I'm not arranging them once they're in. They're not like a president of the team or anything like that. So again, I divide by the things I don't care about. I don't care how they're arranged when they're out. I don't care how they're arranged when they're in. I just care who's on the team. I could just as well count how many ways to make a group of 4. However, now there's a difference. Right? So this would be 765 divided by 3 factorial, that's a 6. So this would be 35 as our baseline. And so if you have multiple choice, you'll know it's less than 35 because some of the groups surely have Bob and Carol together, right? But now we need to take away the groups with Bob and Carol. So a common move you can do if you're going to do something like that is just say, how many groups can I make if Bob and Carol are selected? So I could think about a slot method and say, well, wait, I'm building a team of 3. If Bob's in one of the spots, I don't care which spot because he's not president or anything like that. I just put him in there. And if Carol's in one of the spots, then there's only one more spot left. How many people could be in that spot? Well, I had 7 people. I've chosen 2. There's 5. So there's 5 teams with Bob and Carol. So I'll do 35 total minus the 5 wrong ones equals 30. That would be my answer. So these are some variations you can do with combinatorics. So, is this the be all end all of everything in combinatorics? No. You might have even noticed if you've studied these topics before, we didn't even use the common terminology of permutation and combination. Traditionally, a permutation would be the one where you do care the order. So all these ones I have here would be combinations, and the ones where I'm putting people like first, second, third place would be permutations. The reason I don't tend to use that terminology or get into it or memorize it with formulas with N and K and things like that is because it doesn't handle a lot of the complexities we want to deal with very well. For instance, is this one a permutation or a combination? There could be an answer to that, but it can get overwhelming to think about if there's more than just an in and an out, if there's many different groups. I'd rather just say, put the pool on the top, always divide by the factorial of the outs, and then divide by the factorials of any in groups that you're not arranging further. If you don't care what happens once I'm a security guard, if you don't care what happens once I'm a receptionist, if you don't care what happens once I'm on the team, then you're going to divide that thing out too. And if you know how to do that, you know the main thing you have for combinatorics. And if you combine that with the idea that when you have separate decisions to make, cookies and boxes, I'm going to have a team for the French office and a team for the Malaysian office, right? And how many different combos of teams can work together. Then I'm going to do those separately and multiply them out. Whereas if it's an or, I'd add them, right? If there's like 5 teams I can make in France and 3 teams I can make in Malaysia, I'd say how many total teams can I make? I'd add those, I get 8. But in a lot of the combinatorics problems we're doing, it's about multiplication. It's like, hey, I want one of these and one of these, multiply. Okay. So stuff to play with. Hopefully that was helpful to you. If you want to see more, if you haven't taken one of our classes if you haven't taken one of our classes yet, we'd love to see you. You can visit, this says GMAT, this says GRE, we want the GMAT one. Let me fix that. But we can have you visit any of our session ones as a trial student. And this is a really nice way to check out, see what our class is about, make sure you're a good fit with the teacher. You can visit more than one if it would be helpful to you, make sure that you're finding something that works for you. So we'd love to have you. Stick around if you have any questions. Otherwise, I'm going to close things down here. If you're participating in person, don't forget that, that drawing for the free loot. You can use the link in the chat. All right, everybody. Thanks so much for being here, and best of luck with all your studies. Bye, everyone.